where we left off last week. I've got our notes from last week with our exponent properties, rational exponents, radical expressions, all that good stuff. We're gonna add to these notes, and then I'm gonna have pictures of them all, and I'll put them on our Google Classroom. But oh yeah, all the fraction rules, adding, subtracting, multiplying, dividing fractions. Whew. Yeah, we're going to jump start our brains in again. Oh, let me get my light turned on. It's over here. That'll help. All right, hope you had a great weekend. Great Monday yesterday, getting started back. Things are starting to dry out a little bit this week after last week being so terribly wet. Goodness. But yeah, good stuff. The last day of September. So my goodness, we're zipping right through October. So we're going to be at the holidays before we figure out what's going on. So we are going to jump right into it. Let's take a look at Buzz to see exactly where we're at here this week. Advanced Algebra 2, if we go to our grade screen, as we commonly do, just to see what we're looking at. Let's see, we've done all of Module 1. So if you haven't turned in a test, time's running short. Get that done. I think most people have. There's still maybe some of those that I need to grade if you turned them in last week, towards the end of last week, since I was gone Friday. But I will get those caught up. 2.01. Originally, I had 2.01 and 2.02 last week, but I changed that before class because I saw how much we have in 2.02, and I said I don't want to try to rush through all of that last week. So we did part of it last week and then put the rest of it off to this week. We're going to start on page 4 on that lesson. So we ended up just having the one assignment last week. So as long as you got 2.01, you are current. So this week we're going to finish 2.02 and we're going to look at lesson 2.03. And then there's a quiz over these first 3. So we have a lesson and a half to look at, and then you can do those 2 assignments, and then the quiz is due this week. Next week, we'll look at complex numbers and operations on complex numbers. Complex, think imaginary. Complex numbers have imaginary components to them. But we're going to go to 2.02 and pick up where we left off last week. Got my notes here. We'll take a look at those, getting started out as well. But let's review what we looked at last week, because we're going to start on page 4. I'm going to jump over to page 4 in there. But before we look at page 4, we want to look at our notes from last week. Now, last week we started these exponential properties, the exponent. And we said, okay, if we have x raised to the m power and x being multiplied times x to the n power, we can just add those exponents together, x to the m plus n. So that was our product property. If we're multiplying 2 variables that are the same variable, it can't be x and y, have to both be the same. X to the m times x to the n, we can add them together. We gave an example over here, x to the 3rd times x to the 4th. We can add those together. That's the same as x to the 7th. And we saw down here how that works. X to the 3rd is x times x times x, and then x to the 4th. And when you get all of those written out, you've got x being multiplied by itself, times itself, 7 times. So it is x to the 7th. So that was our product property. We also had the quotient property we looked at. It says if we have x to the m power being divided by x to the n power, we can subtract the exponents. Like x to the 7th divided by x to the 4th would be x to the 7 minus 4, or x to the 3rd. And we looked at that. X to the 7th being divided by x to the 4th. We have several of these. X divided by x is just 1. So 4 of those kind of cancel out because x divided by x is just 1. So it ends up with 3 x's over 1, which is just x to the 3rd. And finally, we looked at the power property. We looked at towards the end of class. We said if we have x to the raised to the power of m, and all of that is raised to the power of n, then we multiply the exponents, m times n. So x squared to the third power would be x to the 2 times 3, or x to the 6th power. And we saw that by saying x squared times x squared times x squared, by raising it to the third power, is x being multiplied by itself 6 times. Let's see, what else did we look at? Here was the important thing last time in lesson 1, 2.01. The key to this whole unit, to doing well on the test, the quiz, the assignments, is knowing how to go from a rational exponent, and a rational exponent has a fraction as the exponent, x to the 3/4. How to convert that to a radical expression. A radical is this symbol right here. We use the square root. This, in this case, this is a 4th root because there's a number out here in the index position. If there's no number, it's just a square root, right? And that's what we're used to. We're more used to square roots than using other roots. But we learned how to convert back and forth. When you have a rational exponent, the number on the bottom, the denominator, is the index for the radical. It means, oh, this is a 4th root. And the number on top stays with the variable and goes underneath the radical, x to the 3rd. So x to the 3rd, the 3 stays with it. We just pull the 4 out and move it outside. And we could go back the other direction. If we were given this, we know that the 3 goes on top and the 4 goes in the denominator. So that's the important part of this whole unit, is knowing how to go back and forth between these two different types of expressions. And so, since we're dealing with fractions, we looked at the fraction properties here, how to add fractions. If we have 2/3 plus 1/4, we have to make these the same denominator. We have to make them both 12ths. And we did that by multiplying this by 1. And this is what 1 looked like. 4 divided by 4 is 1. So we multiplied 2/3 by 4/4, and we multiplied the 1/4 by 3/3. So after multiplying both of these by 1, we end up with 8/12 and 3/12. And then you just add the numerators. Keep the denominator, it's 12, add that. And we talked about, if you didn't know what the common denominator was, just start listing the multiples. The multiples of 3 are 3, 6, 9, 12, 15, 18, right? Because you multiply 3 times 1, 3 times 2, 3 times 3, 3 times 4. The multiples of 4 are 4, 8, 12, 16, 20. And we looked for the smallest one they had in common, which was the 12. Subtracting works just like addition in the fact that you have to have the same denominator once again, except for this time you just subtract the numerators. So instead of 8 plus 3, it's 8 minus 3. So you end up with 11/12 or 5/12. Multiplying was the easiest thing we do with fractions. 2/3 times 1/4, you just multiply straight across. 2 times 1 and 3 times 4. So it's 2/12. And of course, 2/12 we can simplify to 1/6. We did look at simplifying real quick up here. 24/30ths, we could divide it by 1 as long as 1 is 6/6. 24 divided by 6 is 4. 30 divided by 6 is 5. So this is the same as 4/5. And then we looked at dividing, and we said, I said something you probably hadn't heard before. You cannot divide fractions. That's what Mr. Brock says anyway. You can't divide fractions. But you can multiply fractions. So if they ask you to divide fractions, like here's our problem, 2/3 divided by 1/4. It's like, well, I can't do that unless I take the 1/4 and I turn it upside down and make it 4/1 instead of 1/4. Then I can multiply it. So then I'm back to multiplying. 2 times 4, 3 times 1, 8/3. So if we had it the other way around, 1/4 divided by 2/3, we reverse it, make it 3/2, and multiply, and it's 3/8. Again, we can't divide, but we can multiply. So we have to turn that upside down and multiply it instead. So that was the summary of what all we looked at last time. We packed a lot of stuff in. We did some sample problems here, and mainly we're going to finish these properties today. We got another property to add to it to talk about. And we will do some more practice problems. So let's look at our lesson to see what we're adding to our exponent properties. Again, you'll want your pencil and paper out. You want to have a bunch of these notes because this is what's going to make this unit easy for you or make it real hard for you on whether or not you took good notes that you can refer to. All right, so we're looking at patterns of exponents. So we're going to take a look at the pattern that forms when you look at decreasing powers of 4. And I like to do this one on paper as well. So let's say we have 4 to the 4th power. 4 to the 4th power. That is just 4 times 4 times 4 times 4, which we can take a calculator and know that's 16, 64, 256. That's 256. Then if we say we're going to decrease our power and say instead of the 4th, we're going to say the 3rd. So that's just 4 times 4 times 4. Well, since that's 1 less 4, we can just divide this by 4 to know what that is. So because we don't have that 4. So 256 divided by 4 is 64. Right? That's divided by 4 because we knocked off a 4. Now let's knock off another 4. So if we divide that by 4, it's 16, right? So each time we're just dividing by one of the 4s that we're cutting off. 4 to the 1st is just 4. So 16 divided by 4 is just 4. If we want to get back to 16, we just multiply the 4 back, right? Because we're multiplying by 4. But if we go backwards, we're dividing off a 4. So that means 4 to the 0 power would equal what? Well, if we divide this by 4, it equals 1. Well, that works. If you remember how exponents work, if you take anything to the power of 0, it equals 1. If we take 938 to the power of 0, it equals 1. If we take 212 to the power of 0, it equals 1. If we take 4 to the power of 0, it equals 1. If we take Mr. Brock to the power of 0, it equals 1. If we could do that. But let's continue. What if we have 4 to the negative 1st power? Like, oh, now you're getting crazy, Mr. Brock. Well, if this worked, and this is a principle of math that worked, that every time we divide off a 4, we can divide the total by 4. That means this equals 1 over 4, or 1/4. It's like, seriously? 4 to the negative 1st power equals 1/4? Yeah, we can look at that even with our calculator. Let me pull up our calculator here. Let's say, okay, if we have 4, and I'm going to take it to the power of -1. So 4 to the power of -1 equals 0.25, or 1/4. So calculator says that 4 to the negative 1st power is 0.25. So I think we're onto something. What about -2? Well, what's 1/4 divided by 4? It's actually 1/16, which is the same thing as 1 over 4 squared. 16 is 4 squared, right? We saw that up here. And it can continue on as far as you want to go. 1/64, which is the same thing as 1 over 4 to the 3rd power. And if you pay attention and see the pattern that's developing, 4 to the negative 1st power is just 1 over 4 to the 1st power. 4 to the negative 2 power is just 1 over 4 to the positive 2 power. 1 over 4 to the positive 3 power. Notice when it's a negative exponent, it becomes a positive exponent if we move it under into a denominator of the fraction. So this is how negative exponents work. I'm going to go back to our exponent properties and let's talk about negative. So if we have x to the negative m power, that's the same as 1 over x to the positive m power. And if we have, we're going to divide this, 1 over x to the negative m power, that's the same as x to the m as a positive exponent. It works both ways. If it's on bottom and it's a negative exponent, we simplify that to a positive exponent by moving it on top, which means this is really over 1, but we don't write it when it's over 1. Every number is over 1. So if we want to pull in an actual example over here, let's say we have, let's make it kind of complex here. If we have 3x to the negative 4th power over y to the negative 2 power, see, we have a negative exponent on top and bottom. We never want to leave a negative exponent in our answer. So we simplify that. The 3 is just the 3. It stays where it is. But the y, since it's a negative, we want to move it on top and make it positive. And the x, since it's a negative, we want to move it in the denominator and make it positive. Anytime you have a negative exponent, you simplify it by moving it into the numerator or denominator and making it a positive. And we see that works right here. If it's a negative, we can move it into the denominator, becomes a positive. Because this is 4 to the negative 1 power is 1 over 4. The 4 moves down into the denominator and becomes a positive 1. That's a first power. So this is what we added to our exponent properties. How to make a negative exponent into a positive exponent. All right, let's look at the lesson there where it's talking about the same thing. It says, okay, if we have 4 times 4 times 4 times 4, 256, divide by 4, it's 64. And then they take it down to 4 squared and 4 to the first power and 4 to the 0 power, just like we were doing on paper. 4 to the 0 power is 1, because if we just keep dividing by 4, can you see that when the exponent decreases by 1, the value of the power is divided by 4 each time? So in negative exponents, if we divide by 4, we get 1/4. If we have 4 to the negative 2, now it's 1 over 4 to the positive 2, or 1/16, and 1/64th. It continues on. So based on this, we make this rule that I've already put on our exponent properties, that if you have a, let's say a to the n equals a times a times a n times. So if you have 4 to the negative 3rd, for example, it's 1 over 4 to the positive 3, or 1 over 64. And they do some other division there. So 4 to the negative 3rd means takes 1 and divide it by 4 3 times. So they're doing that dividing thing that we were doing up here, dividing the total to figure out what it equals. 0.015625 is 4 to the negative 3rd power, but it's also 1 divided by 64. But what if the negative exponent started in the denominator? Well, that's what we talked about. 1 over 6 to the negative 3 moves up to become 6 to the 3 over 1, right? Or 216 if we simplify it. So they want us to do an example here. Simplify 9 to the negative 1/2. 9 to the negative 1/2. So let's just practice right here in the back where we were working. If we have 9 to the negative 1/2 power. Ooh, all right. Look a little tricky already. We know that we can say 1 over 9 and make that a positive exponent. 1 over 9 to the positive 1/2 power. Then we know that we can convert that 9 to the 1/2 power, 1/2. So the 2 is outside. So this is just a square root. And it's 9 to the first power. So this is the same as 1 over 1/2 power. So 9 to the first power, or just 9. So 9 to the 1/2 power is just the square root of 9. Right? The 2 goes on the outside, which means we don't have to put it. You can, if you need a reminder, this is a square, but without it, it's also a square. So 1 over the square root of 9 is 1/3. So 9 to the negative 1/2 power is 1/3. 9 to the positive 1/2 power is the square root of 9, which is just 3. But this is how we simplify that. We move it to the denominator, convert it to this, so we can see it's just the square root of 9, which is 3, and this is the same thing as this. That's why we need to be able to go back and forth with this property, because this looks like a mess. We still have no idea what number this really is. 1 to the 9 to the 1 over 9 to the 1/2 power. What is 9 to the 1/2 power? It's just 3, because we can convert it here and say, oh, square root of 9. I know the square root of 9. It's 3. I know some of you are thinking it's also a negative 3. We'll get there. Simplifying a power with a negative exponent. So they have a video. We're going to take 6 to the negative third. So we'll go ahead and watch this real quick. See what they're saying about simplifying 6 to the negative third. They may say something differently that I haven't said.
First, apply the definition of negative exponents. 6 to the negative 3 is the same as 1 over 6 to the positive 3. Notice that the base 6 goes to the denominator. When it moves, the exponent negative 3 changes to positive 3. Now you can simplify the exponent as you always have.
And that's it. So 6 to the negative 1/3 is the same as 1 over 216, which is a very, very, very small number. But just move it to the denominator, and that makes your exponent positive. Okay, this is the lesson summary, which means we made it to the end of the lesson. We were close last time, but we needed another 20 minutes or so. Here are those properties we put in our notes: the product property, the quotient property, and the negative exponents. They actually did not put in the lesson summary, which they probably should have. They did not put the power property, because we use that in this lesson, and we'll use that in this unit, being able to raise a power to a power. But they have the other three. They have the product, the quotient, and the negatives. You could print this out if you have a printer and use this page as your notes, but I would certainly add the power property, since they do not have it on the lesson summary. All right, we have a couple more pages, which means they gave us practice problems. Now you try dividing rational exponents. Drag and drop the expressions to show each step of the solution in correct order. So let's work this out first, so we know the correct order. So it says x to the 2/3 divided by x to the 1/3. equals. And they've got it broken out into three different expressions. So we know using our properties that if we have x divided by 2/3 divided by x to the 1/3, that's the quotient property, which means we can subtract the exponents. So this would be the same as x to the 2/3 minus 1/3, because I take the exponent on top and subtract the exponent on the bottom. And that equals 2/3 minus 1/3. They already have the same denominator. So I just subtract the numerator. And then this, as a radical, the 3 goes outside, and it's x to the first power. So there's the three steps. We take this and we change it to a subtraction of the exponents. Then we subtract the exponents, and then we convert it to a radical. Let's see what steps they have. X to the 1/3. That was our second step. There's converting it to a radical. And there was our first step, where we subtract the two exponents. Excellent. Apply the quotient property, subtract and simplify, write using a radical. And then it has another one. Same thing. Subtract those. This is the radical. That's going to be the last step. That's the first step. And that's what you get when you subtract those. So there's 5 problems you can try there. I'm not going to do them all. They're all the same type of thing. Just putting the steps in order. This one just has an extra step because there must be a simplify. Oh, you have to get a common denominator. So there's more problems here. Simplify. Express the answer using a rational exponent. So this says a rational exponent, so we do not convert it to a radical. We leave it as an exponent. So let's write this one down and give that a shot. So we'll have that in our notes. X to the 1/3 raised to the 1/4. So this is x to the 1/3 power raised to the 1/4 power. So our power property told us we can multiply m times n if a power is being raised to a power. So that means here we can go x to the 1/3 times 1/4, which we love multiplying because it just goes straight across, 1 times 1. So this is x to the 1, 3 times 4, 12. And this one said leave it as a rational exponent. So this is the final solution in that. We're looking for x to the 1/12, which is their fourth choice right there. 1/7, 7/12, 3/4. Submit. Excellent. To raise a power to power, multiply the exponent. So they have 5 problems there. And again, it's an exponent to an exponent. So you just go through and you simplify if needed. Choose your answer and go through. So, all right. The third problems they give you here, fill in each box to simplify the expression. So this says if you have 7 to the -2 power. So we'll do that on paper. 7 to the power of -2. We know that's 1 over 7 to the +2, which 7 squared, 1 over 49. Just follow the steps, make it a positive, and then simplify it. What's 7 squared? So that one's not many steps. So the 1a, this would be the 7. 1b would be the power. So once it's moved into the denominator, that's a 2. And it equals, well, 7 squared, 49. Submit. Excellent. See, and there it kind of steps through right there. And I'm betting, yep, there's 5 of those as well. So this one has another step because they change it to a radical. 100 to the -1/2. All right, let's do that one as well. To simplify that, they changed it to a radical. 100 to the -1/2 would be the same thing as 1 over 100 to the positive 1/2, which should be the same thing as 1. They convert it to a radical here because that helps us simplify. What is 100 to the 1/2 power? Anytime you see something to the 1/2 power, that just means take the square root of it because the 2 is out here and the 1 is there. That's just saying the square root of 100, which is 1 over 10. Square root of 100 is 10, right? So 1/10. I know it's also a negative 10. We'll talk about that on the next lesson. So this is 100. This becomes positive 1/2. And then that means 2c out here is a 2. And inside is a 100. And then the square root of 100 is just 10. So it walks you through those steps. Okay, so there's 3 more of those that you can do. Next. Oh, this one's just jump straight to an answer. 1 over 3 to the negative fifths just equals what? So you got to move that to the numerator and then simplify it. Like it. That's a good one. So look at the sample problems on page 6. Use the properties of rational exponents to answer each question. Simplify. Express the answer using a rational exponent. So we do not have to convert it to a radical. And these are being multiplied. X to the 5/7 times x to the 1/7. Remember, our product property says when you multiply these together, you add the exponents. Well, 5/7 plus 1/7 is 6/7. There you go. So this just has 2 problems on this page because there's just 1 problem each. Use what you've learned about negative rational exponents to solve this. So 25 to the negative 1/2. I'll let you do that one because it'll tell you if you're wrong or right. Let's look at the assignment that goes with 2.02. So we'll go to that. Start. Okay. Oh, these are, you have to type your answer. There's 5 questions and they're not multiple choice. So let's talk about this. This is a good one. Is the expression x to the third times x to the third times x third, is that equivalent to, is that the same as x to the 3 times 3 times 3? Do we just multiply the exponents? Why or why not? Explain your reasoning. Rewrite this in, pay attention, this is where it'll get you, simplest radical form. So our final answer should have a radical in it, should not be a fraction exponent. So make that a positive exponent first, convert it to a radical, simplify it, and convert it to a radical. Rewrite this in simplest rational exponent. Exponent. This should have a fraction exponent. And it gave it to us as a radical. So we got to change this from a radical to exponents that have fractions, and then use our rules on multiplying, the product rule, to simplify that. Rewrite this in the simplest radical form. Again, now we got to convert this to a radical. But use our quotient rule first, simplify that, and make it a radical. And then this one, which of the following are equivalent? Here are 4 different expressions. So you need to simplify each of those and see if any of them are equal to each other. Like if A and B are the same thing, you would say, which of the following are equivalent? You say A and B, and then show me how they simplify to be the same thing. Tell me the steps. Look, A simplifies to be x to the 1/2 or whatever it is, and B simplifies to be x to the 1/2, so they're the same. That's that justify your reasoning. I think these are worth 5 points each. If you just say A and B and that's right, you may get a point, but you didn't show me anything. You didn't justify it. It's like, did you guess or did you know? I don't think it's A and B. Now here's what's important on this. When you get to these type of problems and you just go, all right, I'm talking about x to the third times x to the third times x to the third, and that would be equal to, if you're typing that, this is going to get to be a real mess. anytime that you are typing equations, use this button. It says insert equation. If I type this same thing in this, look how that looks. X to the third times X to the third times X to the third. This is so much easier to read, and you will get less confused because it gets real confusing for you sometimes when this starts piling up like this. Like, let's look at this one. If we typed this in, if we said 1 over X to the power of negative 3/6 equals. Yeah, that's not real clear to us exactly what that's saying. But if I insert equation and type that exact same thing, now it looks like this: 1 over X to the negative 3/6 power. Much easier to understand what that is than to try to understand what this is. So make sure you're using the insert equation button when you're typing equations into Buzz. All of these. You're like square root of 4. Yes. If you're like, okay, I don't know how to type the square root of X. If you click insert symbol, there's a whole bunch of help down here. Here's the square root. I'd say square root of X times, and it said the fourth root of X. Well, that's this XY button right here. So there's a Y root of X. So the Y would be 4, and that's X. So look, I can type that square root of X times fourth root of X by using the insert equation button. So make that your habit to insert the equation. But there's 5 problems there that you have to type the answers to for 2.02. All right, let's look at, yeah, I'm going to split that, move on. Let's look at the next lesson because we need to look at how to solve. We've been talking about all this simplifying and converting back and forth, and we haven't talked about really solving any equations yet. So we need to start off by defining what a radical equation is. We need to know what a radical equation is. Like here's t equals 2 times pi times the square root of L divided by 32. This is an equation that will tell you the time it takes for a pendulum to swing to one side and back. This is the time in seconds. L is the length of the string of the pendulum, and 32 is the effect of gravity on it. So this is an equation that does that. And this is a radical equation. So the first thing we need to know is how do we identify a radical equation? So let's put that in our notes. So let me see. I'm going to put it right underneath our exponents. That's a good place to have it. Let's see. Radical equation will be here. And over here, we're going to put what is not a radical equation. So we're going to list over here an example of radical equation. We're going to list over here something that's not a radical equation. So if we have, let's say, the square root of X plus 2 equals 5. That is a radical equation. If we have X plus the square root of 2 equals 5, that is not a radical equation. Look at that very carefully. The difference is very subtle. This one is the square root of 2. The square root of 2 is just a number. It's a number. That's all the square root of 2 is. It's simply a number. So that's not a radical equation. We can pull up our calculator and say 2 square root. Yeah, that's what it is. 1.41421356. That's the square root of 2. So this is just saying x plus 1.41, etc., equals 5. and we would just subtract that, and that's what x equals. This has the variable under the radical. If the variable is under the radical, this is a radical equation. Let's do another example. If we have the square root of x minus 1 plus 3 equals 6, this is a radical equation. If we have x plus 1 plus the square root of 3 equals 6, this is not a radical equation because this is actually a number, 1.7 something. So in order to be a radical equation, there has to be a variable underneath the radical. Variable. This is just a number. There we go. So it's important to know the difference. If we're going to solve a radical equation, we've got to make sure we got a radical equation. So that should help if we have that in our notes to know when we're dealing with the radical equation and when we're not. All right, let's go back. And they will talk about that here. Identifying radical equations. When you click on that, it shows the square root of x plus 2 equals 7 and x plus the square root of 2 equals 7, not a radical equation. And it has a little exercise. Identify, is this a radical equation? Is it not a radical equation? The square root of 3x equals 9. The x is underneath the radical. That is a radical equation. How about this one? Put that in the chat. Is this a radical equation? The square root of x plus 7 minus 2 equals x. We'll see who's left, who fell asleep. Libya says, yes, this is a radical equation. Braylon's with it. Yeah, there's an x that's not underneath the radical, but there is an x underneath the radical. That is a radical expression. How about this one? There's not even a radical in the problem, right? There's nothing. That's just a normal solve for x. Square root of x minus 8 equals 1. Like that one? Square root of x minus 8. Yeah, it's got a square root of x. How about x plus the square root of 3 equals the square root of 5? Right, now these are just numbers. Square root of 3 is 1.7 something or other. Square root of 5 is 2 point something or other. So that is not a radical expression because the variable is not under a radical. X times the square root of 5 equals 7. Oh, let's see if I can fool you on this one. X times the square root of 5. Breland says, no. Square root of 5 is just a number. Square root of 5 is not. This is a no. Because the only thing under the radical is a number. Square root of x minus 11 equals 8. Yeah, that's got a square root of x. So good job. Only when the variable is underneath the radical is it a radical equation. These have radicals, but there's no variables underneath there. Not at all. All right. And this gives you a review of Algebra 1, how to solve for x. We're not going to go through that. When you have x plus 4 equals negative 7, x minus 5 equals 3, we can do that. 4x equals 12. That goes all the way back to Algebra 1. We're not going to worry about that. All right, let's try to solve this right here. Square root of x equals 4. I like this. So if we have the square root of x equals 4, and we want to solve that. We're trying to solve for x. We don't have x. We have the square root of x. So if we want to solve that, to get rid of the square root, we can square it. Right? That's the opposite of square root, which means we have to square both sides. If we don't square both sides, we're changing what the equation equals. The square root of x squared is just x. Those cancel each other out because these are opposite inverse operations, right? And 4 squared is 16. That's the answer. Because we can go back and check it and say the square root of 16 equals 4. Yes, the square root of 16 equals 4. Check. Now, also, we know the square root of 16 equals -4, but when we solve radical equations, we always assume the positive. Assume the positive when we take the square root. We don't use the negative value, taking the square root, when we solve these. So that one works out. It's simply x equals 16. And it shows right here. If you have the square root of x equals 4, you square both sides, x equals 16. Right? And says, how does squaring isolate the variable? Oh, yeah. So we can look at that real quick. How do we know that this actually cancels out? Well, if we have the square root of x squared, that means that's the square root of x times the square root of x, right? Because squaring takes it times itself. And when you have two things like this being multiplied, you can put them together, the square root of x times x. And if you have x times x, the square root of that would just be one of those x's. It's like the square root. If we had the square root of 2 times 2, we know that's just 2. Because 2 times 2 is 4. The square root of that would be 2. If you have two things multiplied times itself, the square root of that is just one of those two things. So this does work. This cancels out this when you have a square root and a square. If we had a third root, we would need to cube it, and that would cancel out. But we're just dealing with square roots. We just want to make sure we know why that works. Page 2. All right, solving radical equations. We're there. We're going to solve some. So let's look at this. It's going to go through the steps, but we're going to work this on paper and get the steps on our own here. So I've written that down. Now they have it in parentheses, but we can put in parentheses or not. There's nothing to distribute. The whole thing is under. They're just making sure we understand the whole expression is underneath the radical. So there are steps to solve radical equations. And the first step is to isolate the radical. Isolate the radical. Well, if we look at this, if I cover up the radical, well, it's already isolated. There's nothing else on that side of the equal sign. That was the only thing on that side of the equal sign is just the radical. So it's already isolated. All right, so that means we can jump to step 2, square both sides. Since our radical is only the square root, we're not dealing with third root or fourth root or fifth root, just square roots, so we can square both sides. So let's square both sides. This we know cancels out, so the left side is just 5x plus 4, and the right side is 7 squared. Okay. The third step is to solve for the variable, in this case x. So we move the 4 over. 5x equals 45. Divide by 5. X equals 9. There's our solution. And finally, we're going to check our solution. And there's a real good reason we do this, because we're going to find sometimes we're going to get the solution, but it doesn't work. Like, what? How can you do that? Well, we'll look at some of that. Let's check it. Let's check our solution. So 5 times 9 plus 4 equals 7. We took our 9, substituted it into our original equation. Now we're going to check to see if this works. So this is 5 times 9 is 45 plus 4. So this is the square root of 49. And the square root of 49 is 7. This works. It's good. That is the solution, x equals 9. Because, remember, we always assume the positive. We wouldn't say this is negative 7. We just say it's the positive 7. That's the positive 7. This works. Okay, we're going to go back to the lesson. They're going to step through the same type of thing. Isolate the radical. In this example, the radical is already by itself. So we can proceed to the next step, which is square both sides. That's where they get the 5x plus 4 equals 49. Now we solve for the variable. We get x equals 9. And then check your work. We substitute it back and find 7 equals 7. So that one wasn't too bad. Let's look at this one. This one's a little different. So this is the square root. The square root of x minus 3 plus 4 equals 1. Okay, x minus 3 plus 4 equals 1. Well, if we remember our steps, the first thing we do is isolate the radical. Oh, these are great to have in your notes, by the way, which you just saw them on our lesson too. So you can go through those four little tabs and write these down. But isolate the radical, square both sides, solve, check. So if you don't have those in your notes, you probably should have had them. So the first thing we said was isolating the radical. Well, if I put my finger and cover the radical, look, that's not the only thing. We have a plus 4 that's also on that side. We need to move that. Move that by subtracting it, right? Because it's added. So that means on the left side, all we have left is x minus 3. 1 minus 4 is minus 3. Now, here is where a lot of students will make a mistake. When I see a mistake solving this, this is one of the most common ones I see. I see a student go, oh, well, I can move that negative 3. Let me add 3 to both sides. You can't do that because the negative 3, is part of the radical. If you need to, put this in parentheses to remember that that all goes together. You cannot do that. If you need that in your notes, no, put that in your notes if you need it. But I see this most often, the mistake I see. You try to move that. No, this is the step where we square both sides because we have the radical by itself. That's the only thing on the left side now. So the left side is x minus 3. Negative 3 squared is negative 3 times negative 3. Now it's not under a radical. Now is when we can move the 3. Say it's just x minus 3 equals 9. It's just an algebra 1 problem. X equals 12. Right? So we got our answer. Now that important step 4, check your solution. So if we go back to our original equation and we put 12 minus 3 all under the radical plus 4 not under the radical equals 1. 12 minus 3. That's the square root of 9 plus 4 equals 1. Square root of 9 is 3 plus 4 equals 1. What? No solution. This is a solution that we found, but it didn't check. So this solution is extraneous. This is an extraneous solution. Yes, when you solve this equation, you come up with a solution, but that solution does not work because it's an extraneous solution. Now, here's where that step right here comes into play. The only way this would work, if we would take the square root of 9 as negative 3 plus 4 does equal 1. But since when you solve radical equations, you always assume the positive root, this doesn't work. That's why this does work as a solution. Because if we would have taken the negative root, it works. But since when you solve radical equations, the rule is you only take the positive root, this is an extraneous solution. Extraneous. There, we'll highlight that word there. If you didn't check your work, you'd say, oh, solution's x equals 12. I'd say, yeah, no solution. Like, this is kind of weird, Mr. Brock. That's why we got to take notes and pay attention, because otherwise, man, we're going to have a lot of fits. All right, so it talks about first thing to do is isolate the radical. We've got this plus 4. So they took minus 4 to move it to the other side. Now we square both sides. We get the x minus 3 equals 9. Solve for x, get x equals 12. And then when they check it, we get that 7 equals 1. This is called an extraneous solution. That's a solution to an equation that does not fit the requirements of the original equation. Kind of weird. And let's see, there's a third example. This third example, I want to work this because we look at this and go, oh my gosh, that looks even worse. It's actually not. This one's actually simpler, probably, than the one we just did. This one's actually not bad at all. At first look, we're like, oh my goodness, look, we got radicals on both sides. Okay. That's okay that we got them on both sides because they're by themselves. They're isolated. If we just square both sides, everything goes away. It's just 3x plus 7 equals 19. And then we can solve for x. So 3x equals 12. Divide by 3. X equals 4. So that's not bad. This is just an algebra 1 problem. Very simple. Solve for x. All right. We just square both sides. But we need to check this. 3 times 4 plus 7 equals the square root of 19. So that is 3 times 4 is 12. And 12 plus 7. Okay, we got the same number on both sides. Square root of 19 equals the square root of 19. I don't know what it's 4 point something if we want to change it to a decimal, but that is just a number. And it's the same. Got it on both sides. So this checks out. This is the answer. So they talk about square both sides, solve for x equals 4. And when you check it, it's correct. It is not extraneous. Not extraneous. Important information about extraneous solutions that you must include in your work. Let's see what it says. Note in example 2, when checking your work, the square root of 9 was taken and found to be 3. That's what I was talking about. If the square root was simplified to a negative 3, it would have checked. However, an assumption is made that square roots will only be simplified to their positive integers. They should have put only in bold. That should be bold and underlined. We're only going to look at the positive roots, the positive integers. Otherwise, you'll always get a solution that checks out one way, but not the other way. That's why you must check your answers in the original equation for each solution you find. You have to. More on solving basic radicals, which means it's another example. So 3 times x plus 7 divided by 12. That's worthy to put in our notes. 3 times the square root of x plus 7 equals 12. At first glance, you're thinking, uh-oh, what are we doing with this? Well, still, the first step, isolate the radical. The radical is not quite by itself. It's being multiplied by 3. See? So if we just divide everything by 3, 3 divided by 3, so this is just the square root of x plus 7, 12 divided by 3. Now it's isolated. There's nothing there anymore but the radical. Square x plus 7 equals 16. Solve for the x equals 9. Now again, let's check it. 3 times the square root of 9 plus 7 equals 12. 3 times the square root of 16 equals 12. 3 times 4 equals 12. We're good. It checks out. X equals 9 is a solution and is not extraneous. So let's see. They're going through the steps. First thing you have to do, divide by 3 to isolate the radical. Then, oh, it's freezing up on me. What's it doing? It's not going through there. Oh, step 2 is over here. Okay. So since you have the square root of x plus 7, you can square both sides to get x plus 7 equals 16. And then in step 3, what does x equal? Subtract 7, x equals 9. Step 4, checking your work. 12 equals 12. All right, here's a you try. There's 6 problems here. Solve this, and which one of these answers do you get? So I'm going to leave those. I'm going to see what other stuff we have before the end of the lesson. But here's some good practice ones, so you know if you know what you're doing, because it'll tell you if you're wrong and tell you what the answer is. 6 problems. Let's go to page 3 here. Quick review of factoring. We got to get to this because this is important. Because we're going to find out, we're going to be dealing with quadratic equations a lot. So if you remember our factoring, if you have a quadratic equation with just x squared, not a 2x squared or 3, just x squared, we need to find the factors of 15, which means they multiply together to be negative 15, but add together to be a positive 2. So what are the factors of negative 15? It could be negative 1 times 15. All right, that's the most simplest one. That would be negative 15. Or it could be a positive 1 times negative 15. But again, if you add these together, that equals 14, not 2. This equals negative 14, not 2. What else can multiply together to be negative 15? The only other things that can do that would be like 3 and negative 5. 3 times negative 5 is negative 15. But adding those together gets negative 2. 3 plus negative 5. 3 minus 5. Could be a negative 3 and a positive 5. This adds together to be 2. So this factors to x minus 3 and x plus 5. Because those are the 2 factors that multiply to be negative 15, but add to be the middle term. So factoring. We're going to be doing factoring in here. Now this takes it to the extra steps. You can also do this the way they show it in our example in the book. Instead of just jumping straight to the answer, they say, okay, we can rewrite this as x squared minus 3x plus 5x minus 15. You may have done it this way, where instead of plus 2x, I'm going to do negative 3x plus 5x, because that's the same thing. I just broke it into 2 different terms. And then you factored by grouping. But what you see, x squared minus 3x, I can take an x out of that and end up with x minus 3. And 5x minus 15, I can factor a 5 out of that, x minus 3. 5 times x minus 3, if I multiply that back together, that gets 5x minus 15. If I multiply this back together, it gets x squared minus 3x. So now I have two terms, and they both have an x minus 3. So I can factor x minus 3 out. And what's left? X plus 5. So look, that's the same answer we got just by using the two terms, x minus 3, x plus 5. But if you need to see these steps on how you get there, that's why this is kind of a shortcut. It's like, that's the two terms. But factoring by grouping gets you to the same place, just a lot more work. Factoring by grouping. But factoring quadratic equations is what we're looking at. So that's what they did. Factoring by grouping. All right, solving radical equations with variables outside the radical. First, we'll look at the one they do on video in our lesson summaries right here. So we'll get a practice some here in just a moment. And I think this is like 4 minutes or something there. It's a pretty long one.
In this problem, you are asked to solve the square root of the quantity x plus 9 all minus 7 equals x. In order to isolate this radical, 7 must be added to both sides of the equation. Since 7 will be added to a variable, the result will be a binomial, x plus 7. Next, square both sides of the equation. Because there is now a binomial on the right side of the equation, it is important to note that the entire binomial must be squared, and not just the individual terms. Remember that squaring a binomial means distributing each term in the first binomial to each term in the second binomial. This problem looks different than the previous equations you have solved. The difference is two different x terms that cannot be combined, x squared and x. To begin solving for the variable, manipulate the equation so that all terms are on one side of the equal sign. This is the standard form of a quadratic equation. ax squared plus bx plus c equals 0, where a and b are the coefficients on the variables and c is the constant. A quadratic equation is an equation with a degree of 2. The degree of the equation will tell you how many solutions there are. But how do you find those solutions? One way is by factoring. By factoring the trinomial x squared plus 13x plus 40, you will find two binomial factors. Set up two sets of parentheses which represent each binomial factor. The first term of this trinomial is x squared. The only factors of x squared are x and x. Therefore, those factors will be in the first term of each set of parentheses. For the second term in each set of parentheses, find the factors of 40, the last term, that sum to 13, the coefficient of the middle term. If it helps, design a chart similar to the one shown. Since 5 and 8 are factors of 40 that sum to 13, these are the two numbers that will be used as the second terms of the factored expression. In the past, when you solved equations, the variable was isolated on one side of the equal sign, while a number was on the other side of the equal sign. However, in order to solve quadratic equations, the equation must be set equal to 0. It is set equal to 0 so that the zero product property may be used. Therefore, in order for the given equation to be equal to 0, the factor of x plus 5, the factor of x plus 8, or both, must be equal to 0. All possibilities must be taken into consideration. If the binomial x plus 5 equals 0, then x equals negative 5. If the binomial x plus 8 equals 0, then x equals negative 8. Whew, that was a lot of work. But it was worth it because now there are two solutions, as indicated by the degree, that can be checked in the original equation. Since two answers were found, x equals negative 5 and x equals negative 8, both of these solutions must be substituted for x in the original equation to see if one or both of them are extraneous solutions. Don't forget to substitute these values everywhere you see the variable. As you can see, only the solution x equals negative 5 checked accurately. Therefore, x equals negative 8 is extraneous, and x equals -5 is the only solution.
All right, there it is. They found two solutions. One of them was extraneous, so it gets thrown out. So the only true solution is x equals -5. X equals -8 does not work. All right, we got 10 minutes. We're gonna try to do a couple of examples at least, so that way we can get a good look at how this works and how we end up with quadratic equations. There's just a review on squaring both sides of an equation and solving radical equations with variables outside. But let's look at the lesson summary and get some practice problems in. Steps to solving a radical equation. Isolate the radical, square both sides, solve for the variable, check your work. There's those 4 steps I had written down, and they're right here in the lesson summary. And this shows you it works a problem as it goes through here. Here's a sample problem. So again, if you have a printer, you might want this as your notes. It's a good example problem to have written down. I want to go to the practice problems they have on page 4. Solve the following radical equations. Select submit to see if you're correct. Okay, this is simple ones like we were doing, but I want to get to some that have the quadratic equations like they were showing. So that may be activity 2. Nope, that's not activity 2. Let's see if we can move on. I want to find one. No, that's not one either. So let's see. Let me just choose an answer and put it up there. Sweet, that actually worked. All right, where's all your ones that have? I'm just going to guess no solution. Say nope, try again. Okay, now it lets me go on. They're not showing us good ones that have. Okay, do they have one back here? We need some that have quadratic equations in there. Solving both sides. Okay, this is a good one. Simplify. So when simplifying this, so the first thing we need to do is isolate the radical, right? That was step number 1. So this -3 needs to go to the other side because it's not part of the radical. So now we've got x minus 3 equals x minus 3. This is the square root of x minus 3, and this is just x minus 3. We want to, now that it's isolated, we want to square both sides. So this side is just x minus 3. But this side is x minus 3 times x minus 3. Right? Which means we got to multiply everything in here to distribute it. So x times x would be x squared. X times -3 be -3x. Then distributing this, -3 times x and -3 times -3. So that's what x minus 3 squared is. X squared minus 3x minus 3x plus 9, which we can simplify to x squared minus 6x plus 9. Now we need to move this over there. Remember, when simplifying quadratics or solving them, you got to set them equal to 0. So everything needs to be on the same side. -x plus 3. 0 equals x squared minus 7x plus 12. Now, does this factor? Are there factors of 12 that will add up to be -7? Well, let's see. The ways we can get 12 is we could multiply 1 times 12. We could multiply -1 times -12. Those would both equal 12. We can do 2 times 6 or -2 times -6. But still, none of those add up to -7. That adds up to -8. We could do 3 times 4 or -3 times -4. Oh, these would add together to be that. So the factors would be x minus 3 and x minus 4. So since either one of those could be 0, x minus 3 equals 0, or x minus 4 equals 0. Add 3, add 4, so x equals 3 and x equals 4. That's our two solutions. Now we need to check those in the original equation. So let's check x minus 3 first. 3 minus 3, right? Plus 3, 3 minus 3 plus 3 equals x, which is 3, equals 3. Well, 3 minus 3 is the square root of 0 plus 3 equals 3. So this is just 3 equals 3. It's square root of 0 is 0. So this one's good. That checks out. Okay, that's a good answer. Is 4 a good answer? Maybe. Okay. The square root of 4 minus 3 plus 3 equals 4. Square root of 4 minus 3, that's the square root of 1 plus 3 equals 4. 1 plus 3. 4 equals 4. This is also a good solution. So we have two solutions to this, and they're both good solutions. Neither one is extraneous. X equals 3, x equals 4, because they both check out in the work. All right, I wanted to get through at least one example there. They have the steps here, so you can go through those steps and see that if you need to go back and look at it again. 3 and 4, 3 and 4, they all check out. Let's look at the assignment because we're running out of time. The assignment for this one, square root of 8x plus 1 equals 5. Solve for x. And is it extraneous or not? Here's another one. Is it extraneous or not? So finding the solution is only half of it. You got to know if it works. Here's another one. This has a plus 7. You have to move first. Here's a problem that Eloise started solving, and then she did something wrong. She thinks both of them are extraneous. So what error? Somewhere she made an error. So start at the top and figure out, oh, wait a minute, you can't do that. She did something wrong. And then here's Violet was going to solve this, right? She was going to solve that. And on her way through the math factory, she dropped all the steps. And she got them mixed up with steps from another problem. What are the steps you need to do to solve this? And there's only 3. Is it A, E, and D, D, B, and A, D, A, and E? Figure out which 3 steps would solve that. And that's it, 5 problems. Let's look at the quiz real quick since we have a quiz this week. Okay, that's just the directions that say do the quiz. The quiz is 1, 2, 3, 4, 5 problems. Rewrite this as a rational exponent. Rewrite this as a radical. Simplify this one using our properties of exponents. Solve this one. And then finally, solve this one. And if it's extraneous, be sure to identify that by showing me that it's extraneous. So again, you have to show all work to get all points. This is 10 points right here. If you want all 10 points, you got to show me how you solve it and show me whether it's extraneous or not. And use that insert equation button. All right, we are out of time. So you just got to pay attention and go step by step. Make sure you got the notes. If you didn't get the notes, go to lesson summaries, write down notes, because you just got to pay attention. This is easy to make little careless mistakes, but if you're able to show me your work and get most of the points, that'll help a lot, because it's easy to make little careless mistakes. So just be careful, step by step. It's not difficult, you just have to follow the steps. All right, guys. This is an A-Day Friday, so we'll only have class again on Thursday. RTI scheduler's already been filled out, but if you've turned in work since then, because I filled it out last week, they're having us put in on Friday. If you've done work and got your grade over 70 since then, I'll count you present. But I can't delete RTI; it's closed, so I can't delete you if you get the grade up. I'll just count you present. So, all right, guys, see you Thursday or next week. Have a great one.